Thank you for the invitation. Today I will tell you about discrete intrinsic volumes and Grassmann valuations. And the first part of my talk is discrete intrinsic volumes. And I should say that there is no probability theory in the first part, but there is in the second part. So wait for it, please. And let's start with a definition of usual discrete volume. We consider the set of all convex polytopes in RD with vertices in the lattice ZD. We call such polytopes lattice polytopes. In what follows, by the word polytope, I will always mean a convex lattice polytope. And for for k-dimensional polytope P, we denote by modulus of P is the k-dimensional volume of the polytope P. And the discrete volume of a polytope P is defined as a number of points, of lattice points lying inside P. And there is two well-known facts about discrete volumes. The first fact is quite simple, and it says that for full-dimensional polytope P, we have such limiting relation. Namely, the discrete volume of nth delayed P divided by n to the power d tends, as n tends to infinity, to the volume of P. And here we use such a property of our lattice ZD that the determinant of lattice ZD is 1. The determinant of the lattice, it is a volume of minimal parallel pipette that form our lattice, and for ZD is 1. That's why for k-dimensional polytope, where k less than d, we have the similar limiting relation, but divided by n to the power k in the left side and normalized by the determinant of P on the right side, where determinant of P, as I said before, is the determinant of the k-dimensional sublattice ZD intersected with affine hull of P. So the second fact about about discrete volume is much more complicated than the first one. The celebrated theorem was proved by Hart, and it states that if we consider the function L of n delayed of P, and we denote it by L subscript P of n, then this function will be a polynomial in n of degree dimension P, which we will call a Hart polynomial. And our first goal is to generalize the notion of discrete volume to the case of intrinsic volumes. It's an important characteristic of polytopes. The definition will be given later. And we want to generalize it so that an analog of our Hart theorem holds. So now we want to introduce the notion of intrinsic volumes. And to begin with, let's define an important class of functions on convex lattice polytopes, valuations. The function phi from the set of lattice polytopes to R is called a valuation if it is 0 on empty set, and for all polytopes P and Q, we have such a relation. In other words, phi is additive function. And in our case, we will always consider translation invariant valuation. Translation invariant valuation phi is such a valuation that phi of t plus p is equal to phi of p for all polytopes P and for all lattice points T. A few words about cones. That we have a k-dimensional cone C, then the solid angle alpha of C of a cone is defined by the formula. We have a volume of the cone C intersected with k minus 1 dimensional unit sphere divided by the volume of whole such sphere. For example, in the left picture, the solid angle of this cone is just a normalized area of this black triangle. And the polar cone of the cone C is defined as a set of all vectors that form obtuse or right angle with any vector from C. On the right picture, you can see example of the cone and its polar. And finally, we are ready to define cones of polytopes. The tangent cone of polytope P at point V in P, we denote TV of P, is defined as a set of all vectors that goes from V inside P. For example, in the left picture, we take a point V in ASH of a polytope, and we take all vectors that goes inside P, and in this case, it's just a half plane. The formal definition you can see in this slide. In the right picture, it is an example of the tangent cone of a polytope at vertex V. Note that for any 2 points that lying inside on the same face, for example, in this case, if we take any points inside the same edge, the corresponding tangent cones will coincide. So we can talk about tangent cone corresponding to the face F of polytope P, and we will denote it by TF of P. And at last, the normal cone of polytope P at the face F is defined as a polar cone of the tangent cone. So now we are ready to define intrinsic volumes of a polytope P. I just want to say that intrinsic volumes generally can be defined for all compact convex sets in RD by several equivalent ways. But for us, it is more convenient to use the formula for a polytope. And the K's intrinsic volume of a polytope P is defined as a sum over all k-dimensional faces of P, solid angles of normal cones at these faces multiplied by the volume of each face. And it can be shown that Vk is a valuation. Moreover, V0 coincides with 1, Vd coincides with the volume of P for full dimensional polytope, Vd minus 1 is a half of the surface area, and V1 is a mean width up to a constant factor. And the formula is given, but it is not clear from it why intrinsic volumes are really important characteristic of polytopes. And there is one argument for studying intrinsic volumes. It was interesting result by Hadwiger that states that for monotone valuation phi on the collection of all compact convex sets in RD, which is invariant with respect to translations and rotations, phi can be represented as a linear combination of intrinsic volumes. In other words, intrinsic volumes form a basis on a space of such evaluations. That's one of the arguments for studying intrinsic volumes. So we are ready to once more formulate our first goal for today more precisely. We want to find a valuation that we will denote AK of P, and we call it the K's discrete intrinsic volume of P, so that an analog of Erhard theorem holds and the following relation holds with K's intrinsic volume in the right side. In other words, we want that AK approximates our K's intrinsic volume for big N. And to solve this problem, let's once again write a formula for K's intrinsic volume. And the first idea to solve this problem is to consider the following quantity, Lk of P. It is a similar sum like the previous, but instead of the volume of F, we substitute a determinant of F multiplied by the discrete volume of F, because the discrete volumes approximate the usual volume, as we know. Indeed, in this case, we have a desired limiting relation with K's intrinsic volume in the right side. But there is a problem with this function Lk, because this function is not a valuation on the set of all lattice polytopes, unlike the intrinsic volumes and the discrete volume. So the key to solving this problem with the function Lk is to consider another way discretely approximate the volume. It is so-called solid angle valuation.
Почему она не аддитивна на границе, что-то дважды учитывается? Целые точки на границе дважды учитываются?
Проблема, yes, the problem is that the determinant is not additive function, and yes, and yes. Okay, and if we consider the solid angle valuation that defined A of P is the sum over lattice points, the solid angles of corresponding tangent cones for full dimensional polytope P, and it is 0 otherwise. Then this valuation A of P will also approximate the usual volume, and sometimes this valuation is more convenient than the usual discrete volume because of the property of complete additivity, as you can see in the slide, that holds for all polytopes P and Q, such that the dimension of their intersection not less than D. And for us, this valuation is important because with this solid angle valuation, we can formulate our first result. Let's define the cast discrete intrinsic volume of P by such a formula. It is a sum over all k-dimensional faces of P, the solid angles of normal cones at these faces multiplied by the determinant of F and multiplied by the solid angle valuation of F. Or we can rewrite it as such a double sum, substituting the expression for A of F. And then, for any k from 0 to D, the cast discrete intrinsic volume is a translation invariant valuation on the set of all lattice polytopes. And moreover, we have that A0 coincides with 1, AD coincides with solid angle valuation. If dimension P is less than k, then AK is 0, and the desired limiting relation holds with cast intrinsic volume in the right side. In other words, we obtained such a translation invariant valuation, AK, that approximates our cast intrinsic volume. And to formulate analog of Erhardt's theorem for these discrete intrinsic volumes, we need some more theory about Erhardt and McDonald polynomials. I will formulate all results in this section for full dimensional polytope for simplicity. As I said in the introduction, the function L, discrete volume of n-zilate of P, is a polynomial in N of degree D, which is called a Erhardt polynomial. Later, Beck and Robbins proved the same result for a solid angle valuation. And corresponding polynomial we will call a McDonald polynomial. There are some known facts about the coefficients of these two polynomials. For example, the leading coefficients of both polynomials are volume of P. The constant term for Erhardt polynomial is 1, for McDonald polynomial is 0. And what's important for us that in 1977, Macmillan generalized Erhardt's theorem to the case of arbitrary translation invariant valuation. Namely, for a translation invariant valuation phi on the set of all convex lattice polytopes, the function phi of n-zilate of P is a polynomial in N of degree dimension P. Immediate corollary from it is that our discrete intrinsic volumes are also polynomial in N of degree K, which we call the cast intrinsic McDonald polynomials. And our second result, it is a theorem about properties of this polynomial. Namely, a full-dimensional polytope P, AKP is a polynomial of degree k with the leading coefficient equal K's intrinsic volume of P with 0 constant term. A0 of P coincides with 1, AD of P coincides with McDonald polynomial, and moreover, reciprocity law holds that connects the values of this polynomial on opposite arguments, namely AKP of minus t equal minus 1 to the power k, AKP of t. And that's all about the first part about discrete volumes. So we found a valuation that we called K's discrete intrinsic volume that approximates our K's intrinsic volume, and so that an Alec-Overhart theorem holds. This is an Alec-Overhart theorem. And the second part will be about generalization of Overhart and McDonald's polynomials. Our goal is to find generalizing function of Overhart and McDonald polynomials. As I said before, we have two ways discretely approximate the volume. It is a discrete volume and solid angle valuation. But we don't know any good connection between these two ways. And our goal is to find a function, generalizing function for both of these ways, which particular cases will be discrete volume and solid angle valuation, or which is the same as the Overhart and McDonald polynomials. And let's start from easy observation that if we consider the full-dimensional cone C that not equal entire space, then the solid angle, as was defined above, can be expressed as 1/2 of probability of non-trivial intersection of a cone with a random line through the zero. And this observation inspired Grunbaum to the generalization of solid angles in the following sense. Let's define the Grassmann angles of C and denoted by gamma k of C as a probability of non-trivial intersection of a cone C with d minus k dimensional linear subspace, randomly chosen with respect to the Haar measure on the Grassmannian of all such subspaces in RD. It can be easily seen that gamma d minus 1 of C coincides with doubled solid angle for C not equal RD, and gamma 0 of C is always 1. Then the natural generalization of both L and A functions can be GK wave that defined as the sum of lattice points, the Grassmann angles of corresponding tangent cones. But there is a big problem of this generalizing function. It's again not a valuation, because in general Grassmann angles are not additive at all. And to solve this problem, we introduce a new concept of modified Grassmann angles. Let's define K's modified Grassmann angle as a probability of non-trivial intersection cone with d minus k dimensional half subspace, uniformly distributed among all such half subspaces in RD. I just want to say that I will not stop here in detail, but these modified Grassmann angles have a lot of good properties that makes it preferable than the original ones. But for us, this concept we will use to formulate our last two results. The theorem states that the function gk of p, defined as the sum over lattice points, the modified Grassmann angles of the corresponding tangent cones, is a translation invariant valuation on p of the t, because our modified Grassmann angles have a good property, they are additive instead of usual Grassmann angles. And moreover, for all polytopes P, we have that G0 coincides with the discrete volume minus 1, GD minus 1 coincides with the solid angle valuation, GD is 0, and if dimension P is K, then our valuation GK forms such a non-increasing chain. We call valuation JK the Grassmann valuation. And once again, using Macmillan's theorem, we immediately obtain that our function JK of nth delayed of P, which we denote G subscript Kp of n, is a polynomial in n of degree d. And the last theorem for today informs us about properties of this polynomial. For full dimensional polytope P and K from 0 to d minus 1, GKP is a polynomial in n of degree d with a leading coefficient equal to volume of P with a zero constant term. Moreover, G0 coincides with a hard polynomial minus 1, and GD minus 1 coincides with the McDonald polynomial. And we call this polynomial GK the Grassmann polynomial. So we obtain a generalization of Erhard and McDonald theorems in terms of Erhard and McDonald polynomials in terms of modified Grassmann angles. We obtain the generalizing translation invariant valuation GK, which particular cases is Erhard and McDonald polynomials. So that's all for today. Thank you.
Okay, so thank you for the nice talk. Are there any questions to the speaker?
А что-нибудь с базисом удается, вот эти самые дискретные внутренние объемы, они базисом будут в множестве всех этих валюаций?
Это хороший вопрос. В смысле, множество каких валюаций?
Ну вот аналог этой самой теоремы.
Хадвигера, да. Ну вот
да.
это тяжело найти именно то пространство. То есть мы думали об этом, но не так много. Вот хочется, да, найти пространство, в котором бы это было базисом. Просто вот в теореме Хадвигера здесь у нас инвариантность относительно вращений есть, а у нас как бы решетка, поэтому у нас нарушается это. Да, инвариантность относительно вращений. Но, возможно, есть вот как раз вот эти решетчатые валюации, в которых они могут быть базисом, и вот надо просто...
Ну там все-таки есть множество тех поворотов, которые решетку в решетку.
Ну да,
там
да. То есть...
перечислимо. То есть, может быть, там что-то и есть, да?
Да, ну вот еще точно не знаем.